Hello, my name is Kobe Kervin, and last summer I worked on a project with Dr. Gordon titled A Strategy for de Novo Assembly of Bacterial Genomes Using Open Source Software. So, the recent rise in next generation sequencing technology has led to a drastic decrease in the cost of whole genome sequencing. But with this decrease in cost comes at a price because there is an increase of errors through per base sequence quality, and then also adapter contamination, which are short segments of sequences that are left over from the sequencing technology. And so next generation sequencing also has shorter reads than traditional Sanger sequencing, and this can make assembly that much harder. And then going off of that, de novo assembly, which is the assembly of genomes that don't already have a reference genome that you can map the reads to, is even more difficult. And so in this project, I was trying to develop a strategy of de novo assembly using open source software so that it could be performed on a desktop computer. And so I used a data set from Chymogen of Pseudomonas aeruginosa, and these reads were Illumina reads. And I first assessed the quality of these reads using FastQC. And as you can see, the per base sequence quality here of the reads was good until I got towards the end, and then the quality started to go down. And so this could be from adapter contamination, like I said, which are short segments of DNA that are left over from the sequencing technology. And so I tested some different adapter trimming technologies to see which one would work the best in this scenario. So I mapped the reads from the original data set to the reference genome that I had. And then I tested 4 different adapter trimming tools: adapter removal, cut adapt, FastP, and Trim-O-Matic. And I found that after I trimmed them using these different tools, that adapter removal had worked the best because 80% of these reads were able to be mapped after I did this adapter removal. So then this is the FastQC of the data set that had been trimmed by Trim-O-Matic, and as you can see, the per base sequence quality remains high all the way through these reads. And then also this is the length distribution of these reads trimmed by Trim-O-Matic. And as you can see, most of these reads are around the 90 to 100 length. And so then I moved on to quality filtering. And so this will filter the reads based on certain qualities for like how good the reads are, the sequence quality. And so I tested 4 different ones of these: BB-Duck, Cut Adapt, Trim-O-Matic, and Sickle. And I found that after I did these quality filtering, most of these mappings were around the same. They only range from about 80.43% to 88.43%. And so I was kind of confused about this. And so I just went ahead and assembled them to see if I could figure out anything from the assemblies. And so after I assembled them, I put them in Quast, which assesses the quality of these genome assemblies. And I looked at different measurements like N50, which is the contig at half the length of the genome. And as you can see, the unfiltered data actually did a lot better than some of these quality filtering tools because the N50 was higher. And for the most part, with the exception of Cut Adapt, it took less contigs to represent the whole genome. So you want less contigs because that means they're longer. And then it had the least number of misassemblies. So I was kind of confused about this, but I think that the stringencies that I set for the quality filtering step could have been too high. So I actually got rid of reads that were good. So that didn't give me a good indication of which one of these tools worked best. So in the future, I want to go back and test these different quality filtering tools on a data set that has more contamination, and then test a bunch of different parameters. And then also in the future, I'm going to move to test some different assemblers to see which of these assemblers would have the best results when it comes to assembling these de novo genomes. Thank you.